is Avery Urea, and I'm a 9th grader at Cottonwood Classical, and this is...
Kiara Namoto, and I'm also a 9th grader at Del Norte High School.
So our project is Albuquerque Fire Department wait times, and we are team number 56.
In Albuquerque, fire departments take too long once they are called to an emergency. This can be dangerous to houses and the surrounding community. Fire stations must have a turnout time of 80 seconds, meaning they must be informed of the call, location, and when unit leaves station, and have to be at the location between 4 to 6 minutes. In 2017, response times were 6 minutes and 40 seconds on average, while in 2018, response times were 6 minutes and 54 seconds. This indicates that response times are increasing, possibly due to population growth and more vehicles on the road. Factors that impact these times are traffic, extended travel, which is when a fire truck must go out of district to handle an emergency, or location circumstances, such as a boundary problem or lack of lanes open.
So this map was given to us by a battalion chief, Justin Staley, and it shows Albuquerque fire departments and the districts they respond to. So Fire Station 22, 15, and 7 are circled, and they're examples of delayed response times and the specific variables that affect them. So Fire Station 22 in the top left corner is located on Unser Boulevard and has slower response times due to the big area they tend to and the need to make extended travel calls. And Fire Station 15 on the right is on the north of the Arroyo del Oso golf course and lacks accessibility routes to the neighborhoods on the south of the golf course, causing delays. And Fire Station 7 on the bottom left corner is located on Central and has to serve compact communities and businesses, which fosters more traffic issues and slower response times.
Obstacles also determine what time the fire truck will arrive. These variables can be cars or other vehicles, stoplights, and location boundaries. An example being the Arroyo del Oso golf course and its neighborhoods that are south of the course, like Los Trechos and Highlands North.
So this year we met with a lot of sources to get information on fire department response times. And Zach Cottrell, who's a civil traffic engineer designer in Albuquerque, has been helping our team for the past 2 years. And he advised us on getting in contact with proper sources from the fire department and other traffic engineers. And he also gave us a map of the whole city of Albuquerque so that we could see where fire departments are located and what streets surround them and may affect their response times. And one of the other sources he led us to was Justin Staley, who is a battalion chief at the Albuquerque Fire Department. And he provided us with a map of fire departments and the districts they're supposed to respond to. So this helped us learn some of the variables that affect response times, and he gave us data on response time averages in Albuquerque and the obstacles they may face on the way to a fire, like traffic, inner fire department problems, navigation, false alarms.
Another resource was Amanda Herrera. She is a part of the Municipal Development Traffic Engineering Division of Albuquerque. She has helped us learn about traffic flow and how certain variables impact the time it takes for emergency systems to get to their destination under a time limit. She also taught us how roads are developed and how they help the fire departments and other emergency systems. And lastly, we learned about opticoms, which have been key to helping us find a solution to create faster response times. Another resource we had was Don Wen. He was one of our mentors. He is a software engineer at Roku in Austin, Texas, and he introduced us to GitHub, which has helped us communicate with him and each other, as well as leading us to use Python and PyCharm for our program as opposed to Logo, which we did last year.
So because our mentor lives in Austin and Kiara and I go to different schools, and right now we're not able to see each other, we use GitHub to work on our code. It's a platform that allows you to share and collaborate your code with other people regardless of their location. So we're able to see the changes we made and document every step of our code changes and communicate the code better in that way. And Opticom is the system Amanda Herrera told us about. It's a type of traffic light that looks for specific emergency systems to turn the light green. We believe it could be a very important for fire departments to bypass the slowdown caused by intersections because the emergency systems could signal for the light to change for them before they even got there. And we also studied Poisson theory, which is a series of discrete events that are known, but the exact time events are random. This is relevant to our project because fire occur at random times and it could help our code be more accurate.
Last year, we used NetLogo, which was based on a networking extension. We were able to place our station at the bottom left corner and have our house that had an emergency randomly generate all over the map. Then it would find the shortest distance possible to get from the station to the house. This program is very simple and helped us understand how important it is to find shorter distances using a program.
So last year we also chose to focus on Fire Station 15, which is located by the Arroyo del Oso golf course, because it lacked an accessibility route to the south neighborhoods. So we wanted to be able to find the shortest and fastest path for the fire departments to get there. In our code, we used a network extension that used a minimum wait to give us the shortest route possible from one node to another.
We also use the Dijkstra's algorithm, which is when you find the shortest distance from one node to another. While we learned a lot from this method, we wanted more coordinates and exact results.
So that being said, one of the things we wanted to do this year was restart our code in Python because it's more flexible and able to simulate the factors that we wanted to investigate and create more real-time data. We also met again with some of our resources in order to learn about recent traffic developments and gather and traffic that would act as the variables that affect response times and make them slower. And our goal was to focus on these variables one by one and see how they could affect response times individually. And we also modeled fire severity to simulate the process fire departments have to follow of deciding which fires are more important to go to first and which ones could wait. And another thing we studied was Poisson theory to have random distribution and more accurately show how fires start and when fire trucks go to them.
So this table on the left explains what standard traffic management is looking for when designing the roads. On the left, it explains what types of movement many lanes and intersections have that are present, and the examples can have different configurations, such as the lane may have several intersections or the volume and number of vehicles present in lanes. The top of the table shows examples of lanes and how they are graded according to these standards. The image on the right shows response districts. These districts determine which fire department responds to what area, but sometimes in certain circumstances, due to lack of fire trucks and people, some fire departments have calls that are out of their own district, which can make response times longer. In our results, we found how to use a clock in our program to get more accurate results that showed how much time it took for the truck to get to the incident. We also were able to see the types of obstacles that impact severity, such as the severity of a fire, can also increase the time. Our next step is to create more programs with different types of obstacles, like other cars, stoplights, and boundary problems, to see how these impact times. We want to incorporate a function that will file out the difference between the current time and when the fire started, getting us a response time. Then try out different maps and new barriers. The image on the left shows how the clock normally functions for every time the spacebar is pushed. And then the second image shows how it can jump to a higher number due to fire severity. In this case, it went from 45 to 83.
So more accurate to specific stations, we discovered that they all need special changes in order to lower their response times. Fire Station 15 by the Arroyo del Oso golf course could use an emergency lane to avoid traffic issues, and they could also use a boundary lane through the golf course to go straight to the houses on the south. And Fire Station 7 on Central could use more Opticom systems to bypass all the delays of the street lights. And Fire Station 22 could use more departments to take care of the big area they tend to.
In conclusion, we believe solutions are needed for a faster way for departments to get to their destination. We believe what will greatly help and understand more about the response times is using Opticoms, accounting for more variables like barriers and number of lanes, and lastly, becoming more efficient in rating fire severity and how taking the shortest and fastest path to the incident can make a difference.
So this year we used PyCharm for our Python code. In it, we imported a maze Pygame to best visualize and simulate a neighborhood that a fire could be taking place. We used a grid or a maze to represent the neighborhood a fire department would serve, and it has cell blocks to represent the houses that they aren't able to go through. At first, we had the player or fire truck automatically be navigated around the map with arrow keys, while the fires are randomly distributed at random times and could only be stopped when the fire truck goes on top of it. However, we changed the program by pressing the spacebar. The fire truck will not move until it sees a fire, and then it will go to the closest fire with the highest severity using flood fill. There are also stoplights incorporated in the code to slow down the fire truck at random points, and a clock that counts every time the spacebar is pushed and is impacted by the streetlights and the severity of the fire to add random amount of time depending on how long it takes for the fire to be extinguished.
So now we're going to show you our code. So I already started pushing the spacebar, but the fire truck stays there because there was no fires that showed up. So right now the clock is at 76, but the fire truck is still at the coordinate of 11. and then it finds the shortest distance to get to the fire, and then the fire raises the severity. So in this case, it went from 82 to 90 with the fire, and then as well it will go to the streetlights, and this will also add time to the clock. So in this case, it went from 91 to 101. To explain more of our code, here is more in depth of what it's about.
So this first one is how we imported Pygame to generate the maze.
So then the second one, this is how we added navigation to the player to make it move based on the arrows on the keyboard.
And the next one is how we added fires and the random severity, which affects the time.
And then here, this is how we use flood fill in our program to get the fire truck to move on its own and find the shortest possible distance to get the fires and the highest in this highest severity.
And this is how we established what the maze will look like and how the cell blocks were placed and to make certain spaces unavailable to go through and obstacles.
And then right here, this shows how we uploaded certain images to symbolize the fire truck, fires, intersections, and the maze.
And lastly, this is how we made the clock and how the severity of the fire increases it, and every time the player moves, time goes up.
And then these are our resources.
Is that it, ladies?
Yes.
Yes.
All right. Question for you. How did you end up forming a multi-school team?
So we had a mutual friend who I actually went to school with and Kiara used to go to school with. And then we just, she actually moved to California. You may know her, her name's Delaney Montoya. And then Kiara and I just met each other and we decided to start working together.
Very good. All right. Judges, any questions?
I had a question on the Pygame. So you started with a maze. Were you able to, where did that code come from initially, or were you able to, what's the source of the code?
Sorry, go ahead, Kiara.
Okay, so we learned from Don. He gave us like it was a online tutorial on how to create a maze in Pygame, and that's where we got it from.
And did that include the flood fill as well?
No, we added that after. So originally we had navigation with the arrow keys, and then we used a flood fill to change it.
Mm-hmm. And how does the flood fill work, kind of, just at a high level?
So when we press the space bar, the fire truck or fires like randomly appear, and then the fire truck will go to the fire by itself, and it will go the shortest path to the fire and then fight the fire, and then another one will pop up and it will go to that one.
Mm-hmm. And does the flood fill is kind of the helping with the routing of that?
Yeah.
Okay. And was it related to before you guys used the Dijkstra algorithm you mentioned? Is that right?
Yeah.
Yes.
How does it compare to that?
It relates because last year we were just focusing mainly on the shortest path, but this year we're trying to find like how long it actually takes, and so it's similar to the same like thought or process or whatever, but we just used it in a different way.
I gotcha. Okay, cool project. You mentioned using GIS maybe next year. Is that like the real road networks? Is that what you're considering?
Yeah, that's definitely something we are considering, because then we could model the roads, and like instead of just like a maze neighborhood, it could be the roads, and then we could model real traffic and things like that.
Mm-hmm.
Yeah.
Okay.
Um,
And next
sorry.
year, if you need any assistance on doing routing on the road networks, we're available up in Santa Fe.
Okay,
Cool, thank you.
thank you.
Thank you.
So this is Sharon DeLand. I was curious how you connected with your mentor.
So we use GitHub mainly, and then we use Google Hangouts to we FaceTime or called him, not FaceTime, but and then we could share the screen just like we're doing now, and then like he would explain what we're doing, and like we would code it, and then he would like whenever we made change.
I think we've lost you for a moment.
Oh, sorry.
Oh, great. I meant more like, how did you meet your mentor?
Oh, so he used to work at Sandia Labs, and my dad actually worked with him, and then he did like the coding and things like that, and then he got a job at Austin, so we had to be able to communicate with him that way.
Yeah.
Thank you.
So how did you get interested in this topic?
So we've always been interested in like traffic problems. And a couple years ago, we did the balloon fiesta traffic. And so then we became interested in like our own community, like traffic problems. And this one was like one of them that we thought was the most interesting.
Okay. Yeah, I remember your balloon fiesta project now that you mention it.
Yeah.
Mm-hmm.
Judges, any other questions? All right. Thank you, ladies. Have a good day.
Thank you. You too.
Thank you.